Hi class, we continue our study in chapter 2 talking about modeling with linear functions by now moving into section 2.3. And 2.3 is going to be talking about function notation and making predictions. So we're going to use that function notation that we've learned in a previous section, and we're going to pull that in and talk about how we use that with modeling, which we learned in the last section. Okay, so what exactly is function notation again? So rather than use an equation, table, or graph or words to refer to a function, okay, remember what a function is. It means there's a one-to-one relationship, or I'm going to phrase that, each input goes to exactly one output. Okay, we learned that in chapter 1. Each input goes to exactly one output. That's what a function is. We name the function. So we use this notation. We use f and then in parentheses of x. Okay, this is read as f of x. So we use this to represent the y variable. So it's just like another way to name the y or dependent variable. Like for example, my name is Matt, but you could also refer to me as Matthew, right? It's just another way to name, um, or just another name for the same thing. That's exactly what this is. Okay, we refer to f of x as this function notation. So to rewrite the equation y is equal to 2x plus 1 using this function notation, you just substitute f of x in for y. So, you just, wherever you see the y, you're just going to replace it with this naming convention. So we're just saying f of x is equal to 2x plus 1. Just another name for y. That's all it is, another name for y. Okay, the notation f of x does not mean, this is important, f times x, all right? It's just another variable name for y. Just another variable name for y. Okay, so think of function as a machine that sends inputs. So I'm inputting in for x, and it gives you the output. So if I tell you what x is, it's going to tell me what the value of y is. It's just like a machine that cranks numbers through. Okay, this is true for any function. So to find f of 4, the input is 4. We are saying to evaluate the function f, so whatever f is, at the value x is equal to 4. So listen to how I'm saying this. You're just going to plug 4 into the equation. You're going to plug your input into the equation. All right, so let's evaluate this function f of x, which is equal to negative 4x plus 2 at 5. Okay, so what we're saying is we're telling you that the x value, the input, is 5. So I'm going to take my function, and I'm going to plug 5 into it. Right, so when I plug 5 in for the input x, wherever I see an x, I'm just going to replace or plug in that 5. So this becomes minus 20 plus 2, which gives me that minus 18 value there. All right, let's do some more real quick. So I've got these functions. F of x is equal to 2x squared minus 3x. G of x is equal to 4x minus 2 divided by 5x minus 1. Now notice how this function is called a different name, or a different letter. You do not always need to call functions f. That's the common notation for it, but you can call it anything. So here I'm just calling it g, and I've got another function, h of x, that's equal to 3x minus 5. So I want to find the following here. I want to find f of negative 2, g of 3, h of a, that's weird, and then h of a minus 2. So I'll talk about those two later. All right, so let's do the first two because they're pretty straightforward. F of 2 means to just plug in negative 2 in for x. When you plug negative 2 in for x, you get the following. Negative 2 squared is 4. So then you get 2 times 4 is 8. Negative negative becomes a positive 6. 8 plus 6 gets you 14. So this function evaluated at negative 2 is equal to 14. Okay, that's another way of saying this is just at negative 2y is equal to 14. G of x here, same thing, just a different function. Plugging in 3, so replace x with 3. 4 times 3 is 12. 5 times 3 is 15. 12 minus 2 is 10. 15 minus 1 is 14. And this 10 over 14 just reduces to 5/7. All right, to find h of a, this is weird, h of a, we substitute a in for x. So just like before we did with the numbers, whatever you're inputting in there, you just replace it in for x in the equation. So h of a, all right, going back, this was my h function, 3x minus 5. So wherever I see an x, I'm just going to replace it with an a. That's it. Now h of a minus 2. So h of a minus 2, wherever there was that x, I'm just going to input whatever that I have value here, which is a minus 2. So distribute, you get 3a minus 6. And then don't forget this minus 5. And minus 6 minus 5 gets me minus 11. Okay, some input-output pairs of a function g, so a different one here are shown in the table. So I've got this table. I'm saying these are the x values, 3, 4, 5, 6, 7. These are the y values, 12, 9, 8, another 9, another 12. Okay, so I want to find g of 7, and then I want to find x when the function g of x is equal to 9. Okay, so from the table we see that when I'm asking you to find g of 7, that the input is 7. So I'm going to find 7 on the table, and that leads to the output. What is the output? So what is the value of the function evaluated at 7? It's just 12 right over here. So to find x when g of x is equal to 9, we need to find all inputs in the table that lead to an output value of 9. So you're going to look along the y values here and see where there's a 9. There's a 9 here, and there's a 9 here. Okay, so we see that both the inputs, x is equal to 4 and x is equal to 6, lead to these values of 9. So the values of x are 4 and 6 here. So it's okay to have two x values. All right, let's do some more. Given f of x is equal to 3 divided by 2x minus 1, let's find f of 4. So again, you're just going to plug 4 into the equation here, right, wherever you see an x. Okay, so f of 4, 3 halves of 4 minus 1. Well, 3 times 4 is 12, divided by 2 gets me that 6. 6 minus 1 gets me that 5. So again, let's do this. Let's find x. Now this is weird. So this was saying to find f of 4. Now this is saying find x. So I'm asking you to find x when f of x is equal to negative 4. So I'm telling you what this f of x is equal to. All right, so you're going to substitute negative 4 for f of x in the equation and then solve for x. So pay attention to how it's being asked here. So I'm going to replace f of x with negative 4. Okay, what I'm going to do is I'm going to multiply everything by 2 to clear the denominators. So 2 times negative 4 is negative 8. The 2's cancel here. You're just left with 3x. And 2 times 1 is just 2. Then what I'm going to do is I'm going to add 2 to each side. So negative 8 plus 2 gives me negative 6. I'm going to divide by 3. And here x is equal to negative 2. So here I gave you what f of x is. And I replaced that in the equation and then solved. All right, you can verify our work in our problems 1 and 2 by putting into a graphing calculator, setting up a table in it, and plugging the values into ask mode. So if you do the following options, you can see here, you would input the x's and it would tell you what the y is. You can fool around with your graphing calculator on your own and try to do that. Working it out by hand is just as good. All right, just be sure you know which values you need to find when you do this. So when you're asked for f of x, what you are looking for is the y values, not the x values. Just make sure of that. All right, let's take a look at this one. A graph of a function f is sketched below. So I've got this function here, right? The line, just so we're clear, ignore all the colored stuff. The line here, the black line here, that is the function. So I want to find f of 4, f of 0. I want to find x when f of x is equal to negative 2, and I want to find x when f of x is equal to 0. Okay, so the notation f of 4 refers to f of x when x is equal to 4, so you're going to go over to 4 for x, because that's telling you the input is 4. So we want to find the value of y when x is equal to 4, so look up, once x equals 4, where does it hit the graph? Well, it hits the graph, boom, y is equal to 3. So f of 4 here is equal to 3. To find f of 0, we want to find the value of y when x is equal to 0. So when x is equal to 0, go look up on the graph, boom, the y value is 1. So the line contains the point 0, 1. So f of 0 here is equal to 1. All right, so we have find x, all right, when f of x is equal to negative 2. All right, so here's what we have to do. We have to go down and we have to find y is equal to negative 2. Well, it's right here. Okay, so we want the original values of x. So look over, we're working backwards here. Look over, where does it hit the graph? It looks at here. So follow this red arrow to show where it hits the graph, right here. And that's at x is equal to negative 6. So the value of x when f of x is equal to negative 2 is 6. All right. If I want you to figure out when f of x is equal to 0, all right, so look where the graph, where the y value is equal to 0. So here's where the y value equals to 0. The point on the graph there, well, that's the x value negative 2. So here, Find x when f of x is equal to 0. Well, that's just a case when x is equal to -2, right there. Okay, some important things. Now we want to get into modeling. The response variable function can be represented by the expression formed by writing the explanatory variable name with the parentheses of f of parentheses here. So the response variable is equal to f of the explanatory variable. So this could be x or this could be t. We use a lot of t in this class. So we call this representation function notation. So your response variable is equal to f of the explanatory variable. Okay, so the way we're used to seeing it is our response variable is y is equal to the function name, and then in parentheses x, that's the explanatory variable. Okay, to make a prediction about the response variable of the linear model, substitute a chosen value for the explanatory variable into the model's equation, then solve for the response variable. Okay, to make a prediction about the explanatory variable of the linear model, substitute a chosen value for the response variable in the models, and then solve the equation. And then what you're going to do is then this solves for the explanatory variable. We'll do an example of both these because it can be weird what I'm saying. Okay, so to find a linear model and make predictions, what you need to do is you need to construct a scatter plot of the data to determine whether there's a non-vertical line that comes close to 2 points. If so, choose 2 points, not necessarily the data points that you can use to find the equation of a linear model. I'll also show you how to do this in your calculator. Okay? Then you want to find an equation of the linear model. Verify your equation by checking that the graph of your model contains the 2 chosen data points, that comes close to all the data points. I'll also show you an example in another video how to do this in your graphing calculator. And use the equation of your model to make estimates, make predictions, and draw conclusions. Okay, so for this one here, I'm giving you the model here. So I'm saying let p equals negative 0.48t plus 71. All right, this be the equation of the model, all right, that models the percentage p. Okay, so that's here. That's telling you this is the response variable of American adults who smoke at t years since 1900. So the t variable for 1970 would be 70. This would be 80. The t variable for 1990 would be 90, and so on. So I have this table here that shows the data. So what you're seeing is that time goes on, the percentage of smokers decreases. And that's a good thing in general, very good thing. Okay, so here's what I want to do. I want to rewrite the equation p is equal to negative 0.48t plus 71 with the function named g. I want to find g of 121. What does this model mean in this situation? I want to find the values of t when g of t is equal to 30. What does it mean in this situation? I want to find the p-intercept of the model. Again, what does it mean? I want to find the t-intercept of the model. What does it mean? Okay, so let's do the first one. All right, so use the naming convention g. We substitute g of explanatory variable. So the explanatory variable is t, time, for p in this equation. So we replace p with g of t. So basically what we're saying here is the percentage of smokers is a function we call g of some time variable, or time being the years since 1900. So to find g of 121, we substitute 121 for t in the equation. So just plugging it in like so. If you plug this into your calculator, right, you'll get g is equal to 12.92. So rounding this, so according to the model, about 13% of American adults will smoke in 2021. The reason we're saying 2021 is because that is 121 years since 1900. And that seems reasonable given the percentages that we had, right? Like if you look here, in 2015, it was 15.1%, and it's definitely fallen. Okay, next one, substitute 30 for g of t in the equation to solve for t. So I want to, basically what I'm asking you is, in what year did 30% of people, were 30% of people smokers? So I'm going to replace 30 there, subtract 71 over. Now I'm going to divide by negative 0.48 here after I do this subtraction. And I get t is equal to roughly 85.42. Okay, so the model estimates 30% of Americans smoked, and you take this t, because remember t is here since 1900, and add to it 1900 plus 85.42. And this is saying, hey, roughly 30% of Americans smoked in 1985. Seems reasonable given that data too. You can verify this using the table application in your graphing calculator as well. So you can plug the equation in, and then if you give the x values, it'll tell you the y values. All right, since the model G of t is in slope-intercept form, we see that the intercept is 0,72. All right, so the model estimates 71% of American adults smoke, well, when t is equal to 0, that's 1900. So research would show this estimate is obviously way too high. So what we're seeing here is that model breakdown has occurred, that's okay. That's okay to get model breakdown. You're going to see the same thing for the t-intercept. So we want to find the t-intercept. So to do that, we substitute in 0 for g of t and solve. Remember, to find the t-intercept, you set the other variable to 0, which would be g of t. Solving this, okay, adding over the 0.48t, then dividing. You get roughly t is 147.92. So the t-intercept is that. Okay, remember the other variable is equal to 0. So the model predicts that no American adults will smoke. If you add 1900 plus this many years, you get 2048. However, do you think there's going to be no smokers in the United States in 2048? Right, that just common sense suggests that this event probably won't occur. There'll still be smokers. So there's another model breakdown. And again, that's okay. Okay, so you can plug the calculator or the formula, the equation in your graphing calculator and use the trace and the 0 option to verify the t-intercepts, and you'll see we did accurately solve for them. All right, so if the function of the form p is equal to mt plus b, where m is not equal to 0, so a non-zero slope, all right, is used to model a situation, then the p-intercept is 0b, obviously. To find the t-coordinate of the t-intercept, substitute 0 in for p in the model's equation and solve for t, like we did in the previous example. Let's do one last problem. The store is open 10 a.m. to 5 p.m. All right, Mondays through Saturday. Let I equal f of t be an employee's weekly income in dollars from working t hours each week. All right, and they're at $10 an hour. So let's find an equation to model this function f. Well, the employee's weekly income is equal to the pay per hour times the number of hours worked. Let's assume no overtime. So f of t, the person's income, is equal to 10 times t, and t would be the number of hours worked. That's pretty simple enough. Let's find the domain and range of each. Well, to find the domain and range of the model f, we consider input-output pairs only when both the input and output make sense in this situation. So time is the input. Since the store opens 8 hours for 6 days a week, the most the employee can work is 48 hours. So the domain here is a set of all numbers between 0 and 48. Like they can't work less than 0 hours per week, and they can't work more than 48 hours a week. But they could work 0 and they could work 48. So that's the domain. All right, the graph here illustrates the domain and range of this model. Okay, so if they work 0 hours, they make $0. All the way up to if they worked 48 hours, they would make $480. Okay, so the domain is 0 to 48, and the range would be 0 to $480. All right, thanks, class.